Hello, welcome back. In last two lectures, we have begun discussing on atomic force microscope. I introduced about atomic force microscope used as a tool to get the topology of the sample surface through the force measurements, and then I discussed little bit about Lennardson potential curve, attractive and repulsive forces between the tip and sample in atomic force microscope, where a physical probe is taken and physical probe is scanned over the surface to measure the force and then to get the 3D image. So, today we will go and discuss, we will be discussing on main components of the AFM atomic force microscope, particularly the cantilevers used in the atomic force microscope and its fabrication method, how the spring constant we have seen in our last class that how spring constant play an important role. So, to avoid snap to contact we should have a higher spring constant, and its resonant frequency is also important. Therefore, the materials to be chosen for making the cantilever is also important, and also that the dimension of the cantilevers, that dimension, materials will all play important roles on the spring constant value and resonant frequency that can be achieved using a particular type of cantilever. So, if we look at the main components of the AFM, I am not if we do not go to much electronics, but just the main parts, then in the heart we have a cantilever probe assembly. So, here is a probe and probe is attached to a cantilever. Sometimes we say probe means probe plus cantilever in AFM atomic force microscope. So, because the cantilever probe can be same material, in many cases it is the same material, mostly silicon or silicon nitride, but it can be also different material. When I mean probe or when I mean cantilever, in these cases that is a same assembly, that is why I have written here cantilever probe assembly. Then optical detection system, we have a laser here. So, a laser light is falling on the back side of the cantilever, and therefore, the back side of the cantilever is coated with a reflective coating. So, that very high reflection of the laser beam will occur, and then reflected beam will go and strike to a position sensitive detector. A detector is taken, photo detector. When the cantilever move upward in the z direction, the deflection or reflection of the light also will move upward in our position sensitive detector, and then we know we can calculate how much it has gone up, the cantilever has gone up. Similarly, then we have a XYZ scanner, the sample certainly it will move in different direction. Sample can be moved in different direction. It can be the tip can be brought closer to the sample, or sample can be taken upwards towards the tip. And then we have feedback loop, is nothing but a type of electronic systems which controls everything, their positioning, movement, etc. So, these are the four major parts in the AFM system, and but the heart of the AFM is the cantilever probe assembly. So, in the cantilever probe assembly, the cantilever is fixed on a silicon base, the holder, and the tip is located on the free end of the cantilever. Now, the curvature of the AFM tip is in the range of 1 to 50 nanometer, 1 to 50 nanometer. The smaller the probe or smaller the apex size, better is for resolution, no doubt. If we take a AFM probe with a smaller or finer tip, then we can have a better lateral resolution, and the way technology is developed, we can have now tip of size less than 5 nanometer. And second thing is that the interaction force between the tip and surface, which is estimated by following the simple Hooke's law, that the force is proportional to the displacement, where through a constant which is the spring constant, or we say it is elastic constant for the cantilever, and del z is the displacement, and the value of the K or spring constant varies in the range of 0.001 to 10 Newton per meter depending upon the cantilever material and geometry. So, if we look at the requirements for the AFM cantilever, there are two major requirements for the cantilever to be used in atomic force microscope. One is small spring constant. In last lecture, I was telling a larger K value will help not to prevent the snap to contact, and here I am saying small spring constant. We will see why, what is good and what is not good. And second requirement is high resonance frequency, preferably greater than 10 kilohertz, and it is necessary for the high scan speed, So, in order to know why this requirement, we have to understand, we need to know, that means how strong force can be measured in the AFM, how strong force, because in AFM we measure the force and that force is utilized for creating the image. Now, to know the how strong force can be measured in AFM, we can first consider the force between two atoms in a solid. Force between two atoms in a solid. In a normal solid, two atoms vibrate with a vibrational frequency of around 10 to the power 13 hertz at normal temperature. So, I can write the vibrational frequency is normally in the order of the vibration frequency of atoms in the solid are in the range of, let us say, I can write omega vibration is equal to 10 to the power 13 hertz. We know this. And typical mass of the atom in a solid is in the 10 to the minus 25 kilogram. Typical mass atom is in the order of m is in the order of 10 to the power minus 25 kilogram. And if we consider the bonds if we consider atoms in a solid vibrate following a simple harmonic oscillator, we can write the formula like omega vibration. If the vibration of the atoms in the it follows the model of harmonic oscillator, omega vibration can be equal to k by m, or k is equal to omega vibration square m, and if we put these values, then we will find this is equivalent to 10 Newton per meter. So, the force constant is coming between the atoms in a solid, force constant, that means vibration is coming, that means spring constant k value is coming in the range of 10 to the approximately 10 Newton per meter. And we know the distance between atoms in a solids are in the angstrom range. The distance between the solids are in the angstrom range. Distance between atoms in solid is in the range of 10 to the power 10 meter. So, if this is the cases, it is in the range of 10 to minus 10 meter, then forces between atoms will become the forces between atoms will be in the nano Newton level, nano Newton range. As you see here, the forces between atoms is in the nano Newton range, and which is expected to follow the Hooke's law. So, now as the force between the solids is in the nano Newton levels, So, similar force should be exerted by tip on the sample surface. If we apply a larger force, then we will damage or break the chemical bond inside the solids, or we can do the destructive analysis. For the if we actually need to do some analysis, destructive analysis, then we can use larger force, but for measuring the surface topology or the surface information, we need force in the nano-Newton range. So, therefore, the cantilever, if a cantilever with a spring constant of 10 Newton per meter is used to measure the force, we need a cantilever with a spring constant of in this range can measure the nano-Newton force inside the solids. Then bending of the oscillation will be also in the angstrom range. Bending also will occur in the angstrom range. As we will see later, we should able to measure the bending of the cantilever in the angstrom level, therefore, able to measure the vertical height or z in the angstrom level. So, here the forces between the atoms are in the nano-Newton level, and therefore, we have to apply similar range of the force by the tip, and that would lead to deflection in the angstrom range, the cantilever deflection, and by measuring the cantilever deflection in the angstrom range, we could know step heights in the angstrom range. So, in order to have the good force sensitivity, so force sensitivity we can write, we know the simple Hooke's law formula, F is equal to k x. So, where we can write del F is equal to k x, x is our deflection, I can write del z. So, now if we have a high we need to have a high force sensitivity, we should have we need a small k value, small is needed for high force sensitivity. In order to have a high force sensitivity to measure small deflection, we need to have a small k value. That is why the small spring constant is preferred or required in our atomic force microscope measurements. And second requirement is the high resonance frequency, preferably greater than 10 kilohertz, and this is required for high scan speed. And we shall see later in the dynamic mode, when the tip is in oscillating mode, tip will be oscillating, and that time in the dynamic mode of operation, in dynamic mode AFN, we will discuss one static mode and dynamic mode. In dynamic mode, tip will be oscillating or cantilever will be oscillating. The signal is proportional to the omega naught divided by k. So, here signal will be more if this resonating frequency is greater, and also k value spring constant will be smaller. And if you remember also another advantage of having a high resonant frequency of the cantilever is that it can avoid the it can become immune to external vibration. If we have a higher resonant frequency of the cantilever or the system, then it will be immune to external vibration. We have seen that in STM, when omega STM is a high omega STM is prepared for getting rid of the external vibration. So, similarly here also having a higher resonant frequency will immune the system from external vibration to a great extent. So, in that regard, if we also we know that as per the basic harmonic oscillator equation, considering moreover what we have seen that small spring constant is good and high resonant frequency is good. Now, considering the basic equation of a harmonic oscillator that is omega, let us say we are talking about cantilever, omega cantilever is nothing but root over of k by m. So, what we see here, achieving these two requirements is not that easy task, because if we have a small k value, then our omega cantilever will be small. So, having if we want to reduce the spring constant, our resonant frequency is going down. Similarly, if the resonant frequency we want more, then spring constant will be more. So, fulfilling these two criteria at the same time is difficult, but it can be done if we have a smaller m, small m values. M is the mass. Here, if we have a mass of the cantilever, here m is the mass of the cantilever. If we have a smaller mass of the cantilever, then we can have reasonably control this, having a smaller spring constant with a reasonably high resonant frequency. If for example, our resonant frequency we need greater than 10 kilohertz, and let us say small spring constant we need 10 Newton per meter for a frequency of omega naught is equal to, let us say we need 100 kilohertz and spring constant of 10 Newton per meter, then we need, then m need to be 1 microgram. So, cantilever of 1 microgram or a very small mass would fulfill this criteria, desired criteria. So, this way we can achieve the requirements to study the sample using AFM. Now, how these AFM probes are fabricated or produced? Normally, two types of probes are used, one is rectangular cantilever and one is triangular cantilever. So, they are either made up of silicon or Si3N4 or silicon nitride. As you see in the probe shape can be of any size here, and these probes cantilevers are of length around hundreds of micrometer. Cantilever lengths are hundreds of micron in length, tens of micron in the width and few micron in thickness. Thickness is very small, and this dimension will play important roles in the stiffness, spring constant, all these values of the cantilever. So, normally as it is mentioned that Si3N4 and silicon materials are used. The technology of microelectronics industry or silicon technology industry is utilized to fabricate the tips or probe for atomic force microscope, and tip can also be generated by forming, as you see here, it is a silicon substrates having a pit here, and then silicon nitride Si3N4 is deposited by chemical vapor deposition technique, and once silicon nitride is deposited by chemical vapor deposition technique, this silicon can be etched away. After this silicon can be etched away. Once it is etched away, we will end up with a silicon nitride cantilever and probe, and we by controlling the thickness of the Si3N4, we can control this thickness, that is normally in the few microns, length, the tip height, aspect ratio, the type of tip, either conical tip or pyramidal tip or any type of tip shape can be produced by this process. So, and the tip shape can have also significant effects on the measurements. As you see in these cases, there are two type of tips. One is a conical tip with a high aspect ratio, and a pyramidal tip with a low aspect ratio. Now, they have important role in the performance of the atomic force microscope. As you see here, because of having high aspect ratio, it can come downward little close to the sample, and also because this thickness of the tip is small, therefore, it could give a better resolution compared to a pyramidal tip, because it cannot come very close to a features of the sample. It has to go move in this range, therefore, here resolution is poor. Similarly, if the here tip shape, if it is a double tip, then if the tip is like this, then it will always be measuring two forces at the same places. If object is one also, because of two tips, we will measure two forces, and therefore, you see the features are looking like a all are double, single features are looking like a double. This is due to artifacts. This little bit of we have discussed while discussing scanning tunneling microscope. And fabrication of cantilever, how cantilever is fabricated. Mostly as we have seen, the cantilevers are made with Si silicon or silicon nitride, and the semiconductor microfabrication technology is utilized to fabricate the cantilever props, and a particular thickness can be chosen, then it can be the rest silicon Si3 and 4 can be deposited by CVD, and the rest of the silicon can be eased away to get Si3 and 4 cantilever. The cantilever can be from single material Si, and that would avoid the strain due to thermal mismatch of different material bonded together in the thin film cantilever. As I told, the Si3 and 4 is deposited on silicon substrates by CVD method, and it is done at a higher temperature. So, at a higher temperature, so there will be a thermal that means a mismatch creating stress in Si3 and 4, and that stress also can have a problem later stage, and therefore, a single material using a single material that could avoid the strain due to thermal mismatch of two different materials when thin film technology is used to fabricate the cantilever. And in addition to that, if all parts cantilever tip are made from a single crystal, it has a high quality factor, Q factor, and that is important for dynamic atomic force microscope. So, how this cantilever prop assembly are fabricated? So, it is started with let us say silicon substrate. Silicon, it is told that here through anisotropic etching. Anisotropic means not isotropic. The etching rate is different for different planes of silicon. So, in this particular cases, a 100 oriented silicon, 00 oriented silicon was chosen first. Oriented silicon pair was taken, and then selectively SiO2 is deposited at a certain places. This is done by lithography. So, what you can do is that first you can deposit SiO2 through, or a silicon can be thermally annealed at high temperature, or wet oxidation can be done. So, that both sides of silicon can have SiO2. Once it is done, as a complete SiO2 layer is formed, then some region can be covered by a suitable resist material. A suitable resist material can be covered some region. After covering the suitable resist material, the rest of the silicon, rest of the SiO2 can be eased away. Sorry. Or sorry, it can be done in opposite way. You can take a silicon piece, then coat with SiO2, either coat with SiO2 by thermal oxidation or by wet oxidation. So, after a continuous layer is formed, then one can put a resist, one can coat the resist, hole through the resist, one can coat the resist material. After coating the resist material, then some region can be removed and other region is not necessary to remove. In this particular cases, some region, this region is removed, SiO2, this region is removed, this region is removed, 3 different region is removed. So, now it is put into a KOH solution, KOH is etchant, and once put into the KOH solution, wherever it see the silicon, it will etch away, but it cannot etch away the SiO2. So, but again anisotropic etching. So, etching rate is high on 100 plane, but low on 111 plane. So, as etching rate is high on 100 plane, etching will be faster in that 100 orientated, but etching will be etching rate will be smaller in 111 plane. Therefore, it producing the facets of 111, as you see here, facets of 111 here, wherever this sides is producing facets. Once it is etched away, a protective layer of Si3N4 can be coated selectively, and after putting the protective layer, then again after putting the protective layer Si3N4, then further etching can be done. This region can be further etched. By further etching, further removing the Si3N4 layer, one can have a complete complete fabrication of a cantilever, silicon cantilever. It is done through the anisotropic etching, and in this way one can control the length, width, thickness of the cantilever and also the tip shape by using this lithography and etching technique. And the characteristic of a FM probe, if we consider, mostly in almost all cases Si3N4 silicon nitride and silicon are used as a cantilever probe in the atomic force microscope. And what we see here, the silicon nitride have a smaller spring constant, less than 1 Newton per meter. On the other hand, silicon has a high spring constant. So, similarly, as per our simple harmonic oscillator formula, again when spring constant is high, resonant frequency will be high, and here spring constant is low, resonant frequency will be low. Again, cantilever lengths are can be of any length one would like to have or one desire to have. Cantilever configuration can be V shaped, single beam, normal tip radius of curvature is here. In case of silicon nitride, it is normally 20 to 60 or 20 to 50 nanometer. Silicon we can have a much smaller tip because it made from single material, no second deposition is occurred, therefore, tip shape is normally smaller with silicon. One can calculate the spring constant, and then spring constant can be calculated from the geometry of the cantilever. So, this is the formula of estimating the spring constant using the material constant or dimension, material constant and dimension. Here E is the Young's modulus, W is the width, L is the length, and T is the thickness. One can using this material constant and the dimension, one can calculate the spring constant, and also if we want a particular type of spring constant value, the dimension can be varied accordingly. There are other ways to calculate the spring constant. One can calculate the spring constant by thermal noise method. Here the thermal noise is a noise of an ideal oscillator is related to the spring constant by this equation, where K is the spring constant here and del Z thermal, T is for thermal, is the mean square of thermal amplitude fluctuation of the oscillator. So, one can measure the oscillator amplitude, that means oscillator means here cantilever, and one can measure the displacement of the free cantilever under a particular temperature at a high temperature, and then from that one can measure the spring constant. Spring constant can be calculated by thermal method. There are other methods also available to calculate the spring constant, which I am not discussing here, but these are couple of methods which are quite easy, quite extensively used to estimate the spring constant of the cantilever. Another factor which is more important is the resonant frequency, cantilever resonant frequency. So, the resonant frequency can be again calculated using this equation. The all values are given here. L is the length of the cantilever, is Young's modulus, J is the inertia of the moment of the cantilever cross section, rho is the material density, and S is the cross section, and lambda I a numerical coefficient in the range of 1 to 100 depending upon the oscillation mode. The cantilever oscillation can be of the different mode, and the values varies from 1 to 100, and this frequency, resonant frequency, is normally in the 10 to 1000 kilohertz range, and it also depends on the quality factor, and the resonance frequency also depends on the which medium the operations to be performed, and because the again medium will also have a role in the quality factor of the materials. So, what in conclusion we see here, cantilever with a small spring constant gives high sensitivity, because of the formula of, as we say, C del F is equal to K del Z. So, a cantilever with a smaller K value can give us high sensitivity, del F sensitivity, and cantilever with high resonance frequency is prepared for fast scanning in addition to the high immunity to the external vibration. So, in order to have a faster scanning on the surface, a higher resonant frequency is needed, and higher resonance, and in order to have a faster scanning on the surface, our tip should not, or probe should not touch the sample. If it touches the sample, we cannot scan fast. So, therefore, in order to have a faster scanning, our tip has to move, tip has to be away from the sample, then only fast scanning possible. And when tip is away from the sample, if it is too far, force will be force of interaction will be small. If it is too close, then the snap to contact may occur. Snap to contact may occur. So, if the snap to contacts may occurs, then it is nothing but a contact mode, and in contact mode we cannot have a fast scanning. In order to avoid this snap to contact mode, we need to have tip little away, but within the measurable force regime, but with a higher oscillation amplitude, If the amplitude or higher acceleration, this force of amplitude or oscillation amplitude higher than the force of the sample and tip, then snap to contact will not occur, and then it will help us to a higher scanning speed. Moreover, with a higher oscillation amplitude gives a better signal, because in case of dynamic mode of operation, this signal is proportional to the resonant frequency of the cantilever. Silicon cantilevers are fabricated using lithography and wet chemical etching. As we have seen, etching is done with a potassium hydroxide solution, and it is anisotropic etching, where the etching rate is faster in 100 direction orientation, where etching rate is slower in 111 direction, and that helps us to produce tip in silicon substrate. The cantilever spring constant can be measured using different technique, what we have covered using the material constant and dimension. Material constant is the Young's modulus and the dimension of the cantilever, and also using the thermal methods one can use, one can calculate the spring constant. These are the main points of today's lecture. For more, you can find these two references book. Thank you.